right here. In here we have to define square of x, returning multiplication of x by itself. Then we have to return the multiplication of pi and the square of the radius, so pi r square. Should be that. Now that we have that definition, we want to get circle area 2, and that should be 2 pi. So 6 point something. No, just 6. 12? Wait. Oh, right, because 2 becomes 4, multiplied by 3 becomes 12, yes. So yeah, begin statements work, they give the last expression, so that works. Have we tried evaluating combinations? I think we've done combinations. Here's some other epic things. Okay, here's another feature. You can't shadow primitives. So primitives like car, cons, CDR, atom, EQ, null, they can't get shadowed. So you can say let multiplication be lambda taking x and y, returning the addition of x and y instead of the multiplication. Then let, because they don't have recursive let blocks yet, let fact be lambda taking n, and call cond eq n 0 1. Otherwise, return multiplication of n by fact of the decrement of n. Fact of 5. Apply undefined function nil. Let multiplication of addition of x and y. Pop. Let fact be lambda taking n. Conditional statement. And see, that's the thing, it doesn't give you descriptive errors just yet. It only works with perfect statements. So this has to be perfect, right? Come on. So many parentheses on this end and how many on there? I'm not sure. What? Okay, I'm going to try very slowly. Let apply undefined function now. Let's let the multiplication sign. Well, let's say. Okay, let plus be lambda taking x and y minus xy. So addition becomes subtraction. In that case, let's do plus 5, 4. It should give us minus 5, 4 if you could shadow it, but no, it still gives you 9. Now let's let add be lambda x and y does something that its name doesn't indicate, so it's something illegal. And let's add impossible quotation marks 5 and 4 to get 1. It gets 1. So regular names can be shadowed, but primitive symbols can't be shadowed. This is because the evaluator, let me show you. The evaluator checks for primitive before it checks for anything else. So primitive overrides something. So as soon as a symbol is found as a primitive, before it even checks the environment, before it even gets to the apply stage, it evaluates to itself, and apply sees the same symbol plus, and not substituted for its value. So it always works. Now we're gonna do a couple of just gonna give a couple of comments here Why is it a hash table? Well, because association lists are slow. O(n) time, in fact. But hash tables are much faster. I don't know how fast, but just faster. And when I use an association list, I get stack overflows because I wrote a recursive search algorithm, and it puts a bunch of stacks for an increasingly growing environment. And when I define big functions, the thing collapses on its knees. And it turns out the neck was made of jelly, and it falls apart, basically, like a house of cards, and nothing works anymore. But with a hash table, at least it works. Now, so this is not purely like SICP. It doesn't actually do stuff with, like, association lists properly. As in, like, or the one, no, SICP doesn't even use association lists. No, SICP does this strange thing where a frame is basically two really long windows. One window has names, and the other window is symmetrical and has values. And they have to do this funny thing where at every function that interacts with the environment, they have to check for the symmetry of the values and the symbols in the environment. And if something doesn't work, it fails, falls apart. But then again, every operation that happens guarantees the sanity of that, so I don't know why it would work that way. But if you do it with association lists, it's impossible to make an association list that doesn't have a member of an association list that doesn't have, what is it called, that isn't a pair. And to be honest, I didn't actually do association lists. I started with 2 con cells per item, because I was stacking lists, so it was really slow. And then it's remained to be slow, even with association lists, and now with hash tables it works. So that's why. But don't worry, we still use lists to get enclosing environments. That's one part. Also, second part, you know, in the beginning when they say there should be a data-directed style for the definition of eval, I took that upon myself. So here you see eval to be a giant cond, just like in the original paper introducing Lisp. Eval has been implemented as a case analysis for clarity using cond. The disadvantage of this is that a procedure handles only a few distinguishable type of expressions, and no new ones can be defined without editing the definition of eval. In most Lisp implementations, dispatching on the type of an expression is done in a data-directed style. So what I did was I got a list. Where is it here? Syntactic forms. And you go to the funds, add syntactic form entry. You get the tag, the name for it. This is just for clarity for the reader. The predicate and the rule for evaluation. I tried this before. And it does a bunch of trickery here with back quotes, but what it does, it splits the syntactic form list and it adds this at the end. And this is so that I don't have to do it in reverse order. I do it in the logical order, which is the same order as it's going to be tested. So by that definition, that's why combination is the last thing, because it's the same way that it is in the actual eval. The combination or application is the last thing, the last entry, because it's the least specific entry. I thought about a different way to do this that always works regardless of order, and that is to get the predicates and to rank the predicates based on how specific they are, to basically rank them by that and then sort them by that, then have that continue to work. Basically just test in that order, in the order of the ranks. That would be pretty cool. I might test that if I understand how to order predicates. Let's also talk about how I added a lot of primitives. These primitives aren't exactly the same way Also, they don't work the same way because I assumed that the syntax might change, and I also didn't want to deal with some primitives taking several arguments. I didn't like that plus could take maybe 7 operands together and reduce them. So I just put 2. Let's see. This is the eval loop. This is the read eval print loop, the REPL. Wow, I have a lips interpreter. Let's see. Also, it does this unnecessary stuff at the end. I forgot to remove that. That's fine. And it has a case for evaluating closures, even though it shouldn't. Yeah, so eval is written in the data directed style that the book was talking about. Took that upon myself because I didn't want to write a large con statement. I found that to be just very annoying. So here you can see it queries the expression and then calls the syntactic form eval rule. I hate long function names. Hate those. And then syntactic form predicate. Also, I know how to use labels. This is nice. Because Common Lisp doesn't do anything like Scheme where you can define inside a define or define inside a define. No, you can't do that. You either have to do define globally or do labels. And it turns out labels is an original keyword that appears in the paper. Let's see here. Apply here. Apply here is really short, and eval here is really short. This is just to demonstrate the actual work. Yeah, the actual work that eval and apply do can be summarized in like 1, 2, 3, 4 lines, and 1, 2, 3, 4, 5, 6, 7, 8 lines. 4 and 8 lines. That's it. That's all you need. That's not long. So that was pretty fun. You can see the rest of the code file is just in implementing all of these functions. I could have implemented some of these predicates, like for example, let these like helper functions, let clauses and let body, as internal with labels. I'll fix that later, but it doesn't really matter. I just wanted to. I coded it in the style of SICP towards the latter end. Eval set expression. Yeah, there's not much to talk about besides that. Also, primitives are in a separate environment. This is really fun. Getting a whole programming language stuck here. So let's get some exercise. Let's try out things that work. Let's go to the chapter running the evaluator as a program. Somewhere along those pages it starts to write some exercises. Some like examples of programs. So, oh yeah, they don't do, what is it, some primitives I already added, kind of cheating. So let's go remove append. I know list takes several arguments, so I can't really implement that in my scheme. I'm going to close this and see lips on the metacircular list. Let's try it. Okay, so define append to take x and y and return if null doesn't have a question mark in this one. If null x, return y. Otherwise, pair or construct from the car of x and the append on the CDR of x with the y. And that's it. This is recursive function, gives us append. If you do append, it gives you the body. Now let's append the lists A, B, C